Alright, this is LAB4 Circuits and Capacitors. Alright, so a little bit of introduction and an explanation of the fundamental principles we're going to use in this lab. So this lab is going to explore circuits in both in series and parallel, and it's going to help us visualize how resistors and capacitors work. Now, here are some of the fundamental principles we have to use, and that is the conservation of charge, which just means that the change in potential across a loop is 0 volts. The conservation of current, which means the current in has to be equal to the current out, and Ohm's law, which is just the resistor is equal to the amount of the resistor is equal to the delta V over the current. So here in part one, we just calculate the charge in you're just going to see the charge in the energy conservation in a series circuit, and it's just a simple series circuit. So the EMF in this case is just two batteries, which are 1.5 volts, so 3 volts total. And we can calculate the current by adding up both of the resistors and then dividing the volts by the resistance, and we get 0.02 amps as the current. Alright, so continuing part one, let's say the ammeter is replaced by a voltmeter. So what happens to the ammeter? Well, the current flowing through would be 0 amps, as the voltmeter has a high resistance, which causes only amount of small current to run through the ammeter, and it's so small it's unable to be measured. So obviously in the voltmeter, it's going to measure all of the change in potential, which is just 3 volts from the two batteries. Now the graph on the right shows the change in the potential across the different varying things. It's shifted a little bit, but the premise is, because I messed it up, but the premise is that every time every time that the current encounters a resistance, then the change in potential will obviously drop until it hits 0. And since these are ideal wires, then it stays flat because there's no change, no resistance on the ideal wires. Alright, so let's continue this. So basically, if a voltmeter is connected across the 100 ohm resistor again, the ammeter is going to read 0.2 amps because that's the current flowing through it right now. But let's say the voltmeter is replaced with an ammeter in parallel with still the 100 ohm resistor. Well, the current won't want to go through the resistor. So it means the current is going to go through the ammeter, and the ammeter is going to read a high current. So we can see that as it reads 0.06 amps. And then there's some calculations for the potential difference across the circuit components, and basically, yeah, that's the calculations there. All right, so now on to part two, RC circuits and charging a capacitor. So let's say we have a battery, a capacitor, and a 10 ohm light bulb connected in series. Then we can observe that the light starts bright and then becomes dimmer, just as if the battery and the capacitor are disconnected. Now, when the battery and the capacitor are connected with a 10 ohm light bulb, then the charging times are those. And then you can see that if you increase the resistance of the light bulb, then the time for the capacitor to charge the light bulb increases, as does the time to discharge. Alright, so part two continued. So basically we can use the data set from the previous, what's it called? Previous thingamajiggy. No, I'm just kidding. When we plotted the time in the seconds, and we used the ln of the change in potential over the initial potential, and so you can see that it's time dependent. And from this, we get the slope of the graph, and the slope is 1 over the RC, so we can calculate the RC from there. And we see that our calculation prediction for the RC and the actual value are the same. They should be the same. Alright, so in conclusion, we saw several observations, mainly that the relationship between the resistors, the currents, and so now there's some conclusion questions. So what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter, and how would it have affected the circuits you hooked it up to? Well, the ammeter in this lab was ideal, so it didn't have any resistance, so it didn't change the current across the whole, like, it didn't change the potential, I mean, across the circuit. So the ammeter would realistically have a certain amount of resistance, so the overall current flowing would be lower. And then what if you were doing this lab in the real life and used the real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this happen in real life? Well, going back to what we said about resistance, the ideal model allows the capacitor to reach full charge instantly because there's no resistor and also no resistance in the actual wires. But we know that in real life there's some slight resistance in the wires and the batteries, so the capacitor would charge slower than instantly. That was my lab, and thank you for listening.